I'm going to pick up on what Ben said, actually. I'm going to try, in the time available, to touch on two points that are complementary but different. One, monitoring and managing trusted systems, but using AI as an assistant within the process, which is like how we solve the current problem. And then the second, slightly more challenging problem, which is how do you monitor and manage AI systems, and are there lessons to be learned from good work that's been done elsewhere? So what I'm going to try and get across here is something of a slightly grandiose vision. It's an ambition of how to do full lifecycle management of trusted systems, and it's a view that we feel very much draws in almost all of the strands that certainly IoTSF touch in, but also some of the more advanced ones that are only just emerging. And within this vision, what we're looking for is a singular sort of trust criteria or trust metric or trust decision method, which applies to all of the key sort of like life cycle points. So we start with the design of the system, and therein comes the secure by design, trusted by design concepts, through to production and manufacturing. Something that I'll come on later, which I think is interesting, is purchasing. How do we manifest the secure facets of a system at the point of purchase? Then key is connection, especially when we look at the secure networking by design in many secured initiatives. How do we provide assurances that the device is trusted before we even let it on the network? Because if we can solve that problem, we're stopping the problem at source. There's then a sort of like a trusted application phase I'll talk about later. And then the last two pieces are really where, as we move more into continuous assurance, zero trust, autonomous response. Because a lot of security is all about that one-shot test. Is it secure, trusted at point of connection? But actually, do you know what? Its trust status changes during its lifetime. So we need to be able to change our behavior. So we need long-term monitoring, life cycle observation, continuous assurance. And eventually, we need a method of doing something about it once we've decided it's non-trustworthy. So it's a very ambitious sort of like full life cycle view of the whole thing. But hopefully, as I go through these slides, you get some sense of how it all fits together. So partly reiterating some of the things that Andrew said before. But so, OK, what do I mean by trust? OK, I don't want to get too philosophical, but let's try and anchor it in some very, very specifics. If we look at that one problem of, I have a device here and I want to connect it to the network. First question, do I trust the manufacturer? I may trust Apple, I may not trust Apple. It's a sort of philosophical relationship you have with the manufacturer, but there's some sort of like brand assurances that are given from certain manufacturers, and you'll just trust everything of that manufacturer. Second question, I think John's just talked about, do I trust it's really from the manufacturer? So that's the spoofing problem, a hard problem in its own right. And actually, to solve that problem, needs some quite sort of like complex stuff. Then you've got to, does the device trust the network? So this is like, is my phone just accidentally connecting to the hotel Wi-Fi? Was that conscious or not? And actually, underneath that, it's not does the device trust the network, does the owner of the device trust the network? And then the inverse of that is, does the network trust the device? And it's not really the network, is it the owner of the network? So there's a complex bilateral chain there involving possibly hierarchies of ownership. Do I trust the device type? So this is the level underneath the manufacturer. This is the individual device. And then you possibly, there's the ability to, has this specific device instance been tested? Like this is like equivalent like PAT testing you might have on electronic devices. A single individual device might go through tests, and that whether it's passed that criteria or not is integral to your decision about whether it goes on. And then you've got device type testing, which is at a different level. Because there I'm not testing the individual device, but I'm saying, actually, we've decided this model 36952 of this webcam is good to go and is always allowed on. And we've got more. So do I trust the software on the device? And in the IoT case, I'd say it's a slightly easy question, because the device often comes as a monolith. It's a singular firmware. But as I move up the chain to sort of like more enterprise or complex systems, if I've got lots of components on this device, then we start to get into SBOM territory in terms of understanding that. How do I know that software has not been tampered with? Because if you don't have that assurance, then actually your other bits fall apart. But again, we know that's a really complicated problem to do with SBOM, etc. Do I trust this device instance? And then again, the spoofing level, and is this device instance really what it says it is? And as we'll see later, that can be quite a tricky problem. And then we move a little bit more to the sort of like the S-bomb and the cherry case, which is, do I trust that this device doesn't have too many vulnerabilities? And also, I might have that assumption at time A, but new vulnerabilities are being announced all the time. So how do I manage that? How does that all work? And these are sort of like the fundamentals that we're trying to address. And just really quickly, trust. It's one of those words bandied around, all right? It needs a little bit of decomposing. A lot of security words like authentication and authorization, it's a very nuanced thing. Who trusts who? All right, it's a big deal. I use my Vodafone, Huawei, Cisco, China Mobile rectangle, Cisco, Vodafone might trust Cisco, and China Mobile might trust Huawei, but I think the opposite is probably not true. And indeed, that lack of trust, in some senses, is government policy. There's a context problem. Trust to do what? A temperature sensor. There's a different level of trust in a greenhouse and a nuclear reactor. Trust because, so this is the transitive problem. This is manifest all over the place in security. It's like dominoes. Like if you keel one over, then the whole thing falls down. And the simplest example is the ownership problem. Often you're trusting the owner of the device, not the device itself. It's a temporal problem. Trust is not one-off. This is essentially what continuous assurance and zero trust is about. But we need lifecycle monitoring. We need continuous assurance to be able to manage that. And there's the legacy problem, which is one of the hardest ones, actually, which is, it's really easy to solve this problem with a greenfield ecosystem, but who has the pleasure of working on a full greenfield ecosystem, especially when you're talking about networks and devices? The stuff's already out there. So that's the ambition. So what exactly can we concretely do about it? So Andrew talked about this already. Personally, I think this new initiative out of NIST has got a lot going for it, partly because we're part of it. We, Inquiring Minds, representing a lot of the work coming out of IoTSF and Many Secured, are one of the 5 sanctioned bills that is working on this problem. And this problem, I think, is a really important problem because it is looking at that full lifecycle problem. So, and why? So why is it important? So, this is just a summary of the key reasons why this is a critical issue. Usability. We know, everyone has experienced, IoT configuration is awful, right? And where the usability is bad, security issues have a tendency to creep in. So we've got to fix that experience. Security fixes, Andrew's mentioned this already. This browser one's a real issue of mine. The fact, even when I connect to my BT hub, I'm going over an unencrypted thing, is fairly serious, because all of that information, my password, is in the clear, right? And that's the de facto standard way most IoT devices are configured, as well as your router. So this stuff needs fixing. It's an opportunity to add security improvements through best practice and modern methods. And this one is, I think, really key one, supply chain. So when I talk about supply chain, I'm not just talking about S-bomb stuff. I'm talking about evidence of purchase, which is one of the things we'll touch on in a minute when we look at the way the NIST stuff's put together. Scalability and efficiency. So, if I'm, a city or a large enterprise and I'm deploying 10,000 devices, I need to be able to configure this zero touch. Otherwise, it's really, really expensive. And I think there's some really interesting opportunities around new business model innovation. If we fix some of these fundamentals, if we add some of these new capabilities, I think it actually opens up new business models, as well as opening the door to some more sophisticated sort of zero trust concepts. So that's the why. So this is, if you care to look at the technical details as they stand at the moment, is the current reference architecture. It basically explains how a device both onboards itself onto the network, possibly also to the application. And one of the big improvements we made to the reference architecture is adding this continuous authorization service. Originally, it was just an authorization service. We flipped that into a continuous service, and thereby, within the reference architecture itself, we're providing the method to continually sort of like monitor the security posture of the devices. And so what does this mean? Well, it means, well, we can physically onboard the device zero touch. We can re-onboard the device. So if it gets wiped, firmware wiped, this is one of the primary use cases it's addressing. It's a very real one. One of the most interesting things about the NIST stuff is it's very Catholic. It's very open in terms of what it's looking at. It's simultaneously looking at these problems at Wi-Fi, Brewski, Thread. So those are three completely different protocols, as well as I think Matt is probably going to be on there fairly soon and a few more sort of like fringe. And it's also got both the enterprise and the consumer use cases in scope, which, as Andrew intimated, are quite different. So it's also looking at so there's one problem, which is, okay, how do I get the device on there? Then the second problem is, okay, what do I do when I'm not happy with it anymore? Because the concept of sending a command to an untrustworthy device, as I'm sure you'll understand, is sort of contradictory. You can't trust the device to behave when you tell it to shut up. So what we need to do is have universal methods at the router level to be able to constrain it and potentially offboard the device. It's also got the concept of application onboarding intertwined with network onboarding. This is quite an interesting sort of like concept, and actually is possibly one of the ways we solve that browser problem. Because the fundamental problem with browser configuration is the browser doesn't have a trusted relationship with the device. If we can add in the browser as an application and bootstrap it into that trust status, then we have a way of solving that. And then I think the other things which is I think interesting from the commercial side is purchasing and supply chain. So I think one of the most interesting things I found in the NIST sort of like architectures that are being developed is the concept that you can use your purchase invoice as security evidence for the device. Because if you think about it, if you've bought something, you probably own it, and you've got a trusted intermediary in the process. And in fact, if everyone's actually used an Amazon Kindle, you'll see something quite similar actually happening via proprietary interfaces by the back door. You'll order it on your website, your Kindle will arrive, and it will magically jump on your network. Don't know quite what black magic is used there or where they're storing those Wi-Fi, but it's a very neat UI experience, and it's quite secure as long as you trust the end-to-end. I think with the stuff that NIST is developing, is bringing the opportunity to introduce some of those concepts in a much more interoperable way. So in terms of, I won't sort of go into massive detail on the specifics, but basically there's 5 core builds at the moment, maybe a 6th one being added shortly. We, as sort of like the many secured, are representing Brewski over Wi-Fi, which is the technical method by which you onboard the network. And there's a roadmap for adding a lot of these more interesting sort of like full lifecycle capabilities as we move forward. And yeah, this is really just an example of exactly how we overlay each and every one of those relatively complicated policy decisions that I talked about right at the start about trust and impregnate it within the onboarding process itself. And yeah, this is just sort of like how you'd normally extract that. So, as far as that work is concerned, all of that is going on and continues to be evolved in open source projects. People are free to join, and as well as sort of like join the sort of like the many secured community where this stuff is talked about. But I also want to spend a little bit of time just dipping a little bit more into that Morello cherry vulnerability problem, because it's a lot of what I talked about might be a little bit abstract. Hopefully this might collapse it down and make it more transparent why we think this is important. So, as as Andrew said earlier, and a few of the speakers, like Richard from ARM, this new cherry concept is a way of developing new, secure, memory invincible hardware. Right? So what? Who cares? Right? How do we make that enhanced secure capability and surface it from an operational and economic perspective? So, the basic logic is, well, SBOM describes my components. And if I use SBOM and look up the CVEs, that's essentially both the live and historical vulnerability surface of my device. So if I use one of these funky little chips, in theory, my vulnerability surface, my attack surface, has now collapsed by 70%. This is quite a big deal, right? But how do I now make use of that information? So let's now put that back onto the life cycle. So, well, firstly, you insist on the design principles at the, when you're actually creating the device and manufacturing production. So that's the use of the cherry-type concepts and the cherry-type hardware. So the next obvious one is point of purchase. So how do I evidence at the point I'm trying to buy something that this device has got a lower vulnerability surface than something else? So if we can daisy chain this evidence hierarchy that we discussed, we can turn this something very specific and very concrete with numbers on it and pointing to vulnerabilities. So these abstract sort of like claims of enhanced security become very, very real. And then the next useful stage to be able to surface it is a point of connection. If a memory unsafe device cannot connect to the network, then we've got a very clear way of evidencing the value and the economic viability. And then downstream, the inverse of that is, OK, a new vulnerability gets announced, like the OpenSSL. So if I'm not memory secure, I've got to put everything into fifth gear and sort something out quickly. If I am memory secure, I can sit back and relax. So again, it's another way of surfacing that sort of value add. So in terms of what does this look like concretely, so actually upstairs on one of the stands, we've got a little demo that sort of hopes to get across some of these concepts a little bit more clearly. And in fact, it's a very specific example of a tool chain, which given any theoretical device, software set that's got a set of build instructions, it will compute using SBOM what the vulnerability surface is. It will then also compute what value you get from using a memory-safe architecture. So it's turning these abstract notions into something sort of very real that you can write a report on and point to particular CVs and thereby actually start to build up the true economic argument for how this works. So, why AI? A lot of what I talked about in terms of that lifecycle management and building up the sort of the trustworthy assessment through the full lifecycle, there are all sorts of flavors of clever cryptographic algorithms and data sets and certificates that provide that. But it doesn't work right across the board, and it doesn't work to legacy. And this is where we come back to sort of one of Ben's points sort of earlier, which is, OK, so how does AI help? Well, to be honest, you can't do it without AI. Basically, there are sort of three core concepts that you need to do. You need to build up the evidence of trustworthiness using the best sort of cryptographic evidence you've got. You've then got to plug in the holes with heuristics, analytics, and the top-end AI algorithms. And then once you've made those assumptions, and some of those assumptions are going to be wrong, and some of those assumptions will change, you need principles in place to continuously monitor and address that. So I've just picked up sort of three of the dimensions. Device identity, what is this? Device type, what are you? Device type behavior, what should I expect you as a type to do? What are the components? What are you built from? And what vulnerabilities you've got? I mean, 5 very simple questions, the same ones I asked right at the start, all essential if you actually want to assess, should I trust this or not? But how do I make a decision? And basically, it's a mixture of best of breed cryptographic proofs that you got, use some funky AI stuff, and there are all sorts of different forms of this to plug in the gaps, and then put in principles to continuously monitor and correct. So I've got about 4 minutes to the other bit, which is the AI bit. So that covers the trustworthy IoT systems and how AI can potentially complement this. And now I'm going to touch on the other question, which is, OK, AI systems, they're going to be quite complicated to monitor and manage. What can we learn? So essentially, we've got a continuum of complexity here. I think I touched on this in the panel earlier. IoT, well, I've probably convinced you, or you knew already, the security problem is already hard on IoT. But that's a simple problem, right? Your software's a monolith. Generally, your upgrade path is linear. You generally go up 1 versions, or potentially you go back. And you generally, for simplicity, your behavior is relatively deterministic with maybe a few config parameters. You move up to enterprise software, instantly it gets more complicated. You start getting in the SBOM problem. Your enterprise system is made of lots and lots of components, each of which has got a different upgrade path. That creates a combinatorial problem in terms of like versioning. It's got lots of dependency problems. One component is dependent on another component, and each of those components might have vulnerabilities. By the time you get to an AI system, it is so much worse, because you inherit all the problems of enterprise software, but then the behavior of the software is determined by literally billions of parameters. And not only that, the behavior of the ensembler has a core sort of dependency both on the training data, the validating data, the system that it's running on, the system that it's been trained on, and the system that it's been validated on. So it's a really, really knotty problem. And it's early days, and as I think we said earlier, we did run a couple of workshops in the summer with a broad sort of like TechWorks community, so not just the IoTSF community, the NMI community, the ASIN community. It is very well attended. And the white paper is yet to be fully written up on that, but will be coming shortly. And really it comes down to three problems, or we think there's three sort of foundational bits of tech we can introduce to help solve this problem. Version it, right? I made this point on the panel. I need to be able to have a method of pointing at an AI system and know it hasn't changed. It might have infinity of behaviors, but you know, at the moment, if you're running ChatGPT, they can silently upgrade the stuff behind the scenes, and you get a totally different behavior. So, what's the point of making any claim about its behavior, about its sort of capability, its competence, its fairness, all this type of stuff, if you cannot strictly version it? The second question is, okay, an AI system's actually got lots of authors. You know, it's got the person who trained it. You've got the person who like configured the algorithm. You might hear another person that deployed it. But you need to allow the author to make claims about the system. But then you also need the ability, possibly not to totally trust the claims that the author made about the system. So you need a system that will also support what we call auditor claims, but this could be testing, compliance, any sort of third-party validation. And really what we're looking for is a unified framework in which we can manifest each of these sort of like capabilities, basically repurposing some of the device descriptors technology that Andrew talked about in his talk. And this is sort of like really just saying the same thing using a different diagram, but explaining the full complexity and the number of dimensions that change, but also the ability to both label, to version, author, and attest to each of those issues. So just in summary then, on the IoT side, hopefully we've managed to emphasize that there's a clear need for some consolidated notion of trustworthiness that is pretty universal. And you know, if nothing else from this talk, I'd advise you go and have a look at the NIST work. I think it's going to be quite important, and it seems to be some good work where some of these problems are being concretely addressed, not abstractly with policy, very concretely addressed. And we're fortunate in being able to promote some of the managed secured work and help direct that work. And I think within that context, key foundational innovations like Cherry, suddenly their value gets surfaced, right? Because this is why we're sort of quite passionate about these sort of concepts. You know, if you believe what says on the tin, the Cherry stuff, you know, kills 70% of vulnerabilities, then this is fantastic. This provides us a full lifecycle management framework where we can surface the economic value of that. And then going on the AI side, well, it's a complex notion. I think we've already clearly identified that, but I think there's some very simple things that we can do to help solve this, drawing on best practice from sort of like the IoT and wider cyber community. Very simply, we need versioning, we need rigid versioning, we need author claims, and we need auditor claims. If we have those in place, it doesn't solve the problem, but it gives us some like solid foundations from which to work from. And with that, there's my contact details, and I'll be around over lunch. Thank you.